Good day and welcome back to the third part of our discussion on Newton's methods. So just quickly, the overall reminder, when we are using Newton's method, our goal is to approximate a root or a solution to the equation f of x equals 0. And Newton's method itself is an iterative scheme that hinges upon an intelligent choice for x1, which we think of as kind of an initial approximation for the root. We then take that initial approximation x1 and we use the scheme or formula above to get a list of approximations, x2, x3, x4, and so on. And the idea is that at each step you should be getting a better and better approximation to the value of the root. Now note, as we indicated in our previous examples, Newton's method will not always converge to the root. There are subtleties. Sometimes, for example, it will converge, but it will do so very slowly. So depending upon the quality of our initial guess x1 and the function itself. So you may need more or less kind of iterations or computations to get to that desired level of approximation. So let's finish up our discussion on Newton's method by exploring a slightly more involved but a very typical example that's used Newton's method to approximate the 6th root of 2 correct to 8 decimal places of accuracy. And note that this really leaves a lot to the reader. In order to use Newton's method, the first thing that we would need is a function to apply it to, along with an initial guess. Secondly, we might be wondering, how do I even know if my approximations have this 8 decimal places of accuracy? And that's maybe the easy part for us to explain. Ideally, at each step, your approximation is becoming better and better. So once you get to 2 approximations in a row that agree to 8 decimal places of accuracy, that means you can stop. And of course, that's going to require us to use a calculator. But let's get back to that initial question. In order to approximate the 6th root of 2, we need to think of a function f that has the 6th root of 2 as a root. So what I want you to think about for a moment is, what would you have to do to the 6th root of 2, kind of algebraically, think in terms of raising powers, adding and subtracting, to get back 0? If we start with the 6th root of 2 and we raise it to the 6th power, then that number would simply be 2. Which means if we raise it to the 6th power and subtract 2, we would get back 0. And that's just a not so fancy way of saying the 6th root of 2 is a root of the polynomial x to the 6 minus 2. So by thinking of a function that would have the 6th root of 2 as a root, we now have a function we can apply Newton's method to. But in order to apply Newton's method, we need an initial guess. So thinking about the 6th root of 2, or even just the square root of 2, what might be an initial guess that you could come up with? And the initial guess I'm going to suggest, and it's not the only initial guess, it's just a very reasonable one to get started with, and we're going to guess x1 equals 1. And how I would come up with that is what? The square root of 2 is 1.414 something something something. The cube root of 2, the 4th root of 2, those are all values within a reasonable distance of 1. So let's just use that as our initial guess, a nice round number. So if x1 is 1, x2 is going to be x1 minus f of x1 over f prime of x1. So f of x is x to the 6 minus 2. F prime of x is 6x to the 5th. And putting this together, x2 is going to be 1.166666667. And I have just simply substituted in 1 to the desired functions and put it into my calculator. And I'm going to keep doing this process over and over again using this generic formula that we have for Newton's method. So I'm using my calculator. So when I use my calculator to get x3, I would have 1.12644,368. x4 is 1.12249707. And observe that I am tracking to 8 decimal places. And once I have 2 of these iteratives in a row, say x3 and x4, if they were to agree in all 8 decimal places, we would have that desired accuracy. At this point, I can say it appears that x4 is correct to at least 2 decimal places of accuracy. So continuing on, still using my calculator, I find that x sub 5 is equal to 1.12246205. And at this point, the most we could guarantee is maybe 4 decimal places of accuracy. So we continue on. And remember, depending upon our initial guess, depending upon the function itself, it can take more or less computations. It's reasonable that we might have to go up to even 10 or 12 approximations before we get that desired agreement. But in this case, we don't have to. X sub 6 is also 1.12246205 rounded off to 8 decimal places. So since we agree to 8 decimal places of accuracy, this is where we stop. So we've been asked to approximate the 6th root of 2 correct to 8 decimal places of accuracy. So the last thing we do is present our solution. The 6th root of 2 is approximately equal to 1.12246205. And this completes our discussion of Newton's method. But remember once again overall, what does Newton's method do? It does not solve an equation of the form f of x equals 0, but instead what it does is it approximates the solution to an equation of that form, and it's an iterative scheme. What that means is we start off with an initial guess x1, and we use that to generate a list of approximations, with the idea being each approximation is going to be better than the preceding one. That is to say, x5 is better than x4, x6 is better than x5, and so on. And when do we stop? Well, when we've reached what we consider to be the desired level of accuracy, which can depend from problem to problem. And for the moment, this is going to wrap up our discussion of not just Newton's method, but differentiation. In our next section, we will begin to explore a seemingly unrelated question of finding areas enclosed between curves, but if we stick with it for a few sections, we'll see the connection back to differentiation. So stay tuned and take care.